This is example 4. I think we're on example 4 for optimization. This problem is a little different from the others in that we are given the equation of a parabola, and you can look at the figure there, and we're asked to find points on the parabola that are closest to the point 0, 2. So we're going to set up this problem in a similar way, but the equations that we want to optimize are going to be a little bit different than our geometric equations. So we go through what we're given, well, the equation of the parabola and the point that we want to minimize the distance to, and we want to minimize the distance from 2 points on the curve to that point 0, 2, and of course if you draw the diagram it's much easier to visualize. So how do we get an equation for what we want to optimize? Well, we're trying to optimize the distance between the point 0, 2 and some point on the curve, that point being the point that's closest to 0, 2. So remembering back from algebra, you had a formula for finding the distance between 2 points on a curve, and that's a good place to start to get an equation to optimize. That's basically what we want to optimize. We want to minimize that. And our constraint is that the points we're looking for do have to fall on that parabola, so they can't just be anywhere. If we take that equation of the parabola and we solve it for x squared, so x squared is equal to y minus 1, we can plug that into our distance formula to build our constraint into the distance formula. We can also plug that point 0, 2 into our distance formula because whatever point xy we pick on our parabola, we're looking for the distance to the point 0, 2. So now plugging that information into our distance formula and then substituting y minus 1 for the x squared so that we end up with a distance formula that just has one variable in it, which happens to be y, and I know that's weird because we're always used to working with x, but in this case it just worked out easier to create an equation that only had y in it. If we take our distance formula and we square both sides of that equation, we get d squared is equal to y minus 1 plus y minus 2 squared. And that's basically the formula that we want to look at. So let's call d squared, let's just call that capital D. So we have the function d of y. And now this is the equation that we want to minimize. This is our distance formula with a built-in constraint. So we're going to take the first derivative like we normally do. And if you want to use the second derivative test, which I'm going to do here just for the heck of it instead of the first derivative test, you can go on and find the second derivative. And since the second derivative is just 2, that is always positive. So that means we have an absolute min. And so then if we solve, we get y is equal to 3/2. So we're looking at the point y, the coordinate 3/2, and if we plug that 3/2 for y into our x squared is equal to y minus 1, we get that x is equal to plus or minus 1 over the square root of 2. So we have found our 2 points, 1 over square root of 2 3/2 and negative 1 over square root of 2 3/2. And that's it.